Have you ever really thought about what happens in a tiny, tiny sliver of time after you hit send? Well, today, we're going on an adventure. We are going to follow one single piece of data as it travels from your computer out into the world and to its destination. Let's get into it.
You know, it really does feel like magic, doesn't it? You tap a button and poof, information just appears on a screen maybe thousands of miles away. But it's not magic. It's this incredibly fast, totally invisible ballet of technology. So, how does it actually happen?
To get our heads around this, we're going to meet our little hero for this story, a single data packet. Think of it like a tiny digital messenger. It's carrying a little piece of your email or your photo or whatever on this epic mission across the internet. So let's follow its journey.
Now, our packet's journey doesn't just start out on the massive global internet. Nope. It begins right there, inside your own local network, your home, your office. And its very first challenge? It's got to find the front door, which is your router, the device that connects you to the whole wide world.
So the first gatekeeper our little packet meets is something called a network switch. And this device, it keeps a really special list called a MAC address table. Just think of it like a local address book. It knows every single device that's connected to it, from your computer to your phone, even your smart toaster.
And here's the best way to think about it. The switch is kind of like a teacher in a classroom who knows exactly which student is sitting in which chair. So when a note comes in for, say, Sarah, the teacher doesn't just shout it out to the whole class, right? No, they walk over and hand the note directly to Sarah's desk. The switch does exactly the same thing for our data packet. It sends it only where it needs to go. No shouting necessary.
So you might be wondering, how does the switch build this seating chart in the first place? Well, it's a really clever observer. Every time a device sends out some data, the switch looks at where it came from and it just makes a note. It says, okay, that device is over there. Now, if it gets a packet for a device it's never seen before, it has to do the one thing it tries to avoid. It shouts to the whole class. It sends the message everywhere. But the second that device replies, the switch immediately adds it to the list, and it never has to shout for that device again.
Okay, so our packet made it past the switch and got to the router. Now it's facing a much, much bigger challenge: how to navigate the absolutely gigantic map of the internet. It needs directions, and it turns out there are a few different ways to get them.
Let's start with a classic. This is one of the original GPS systems for the internet, and it's called the Routing Information Protocol, or just RIP. You can think of this as the old-school way of asking for directions.
The way RIP works is actually really simple. A router running RIP doesn't have a full map of the internet, not even close. Instead, it just asks its direct neighbors, hey, how far are you from the destination? And it trusts what they say, and then it just picks the path that has the fewest hops or stops along the way.
But this method has a huge limitation, and it's this number, 15. A network using RIP can't have a path that's longer than 15 hops. If the destination is 16 routers away, RIP just gives up. It considers it unreachable. It's like a delivery service that just straight up refuses to go more than 15 blocks from its warehouse.
And there's another problem: speed, or lack of it. Routers that are using RIP only bother to share updated directions with each other every 30 seconds. Now, in internet time, 30 seconds is an absolute eternity. If a digital road suddenly closes or a brand new shortcut opens up, it can take way, way too long for everybody on the network to get the memo.
So, yeah, pretty clearly, for the internet we use today, just asking your neighbors for directions is not going to cut it. We need something way smarter. We need something like a real-time GPS that can see the whole map and can instantly reroute you around a traffic jam.
And that is exactly where dynamic routing protocols come in. These are the super intelligent systems that really power the modern internet. Instead of just blindly trusting their neighbors, routers that use these protocols all work together to build a complete, constantly updated map of the entire network.
And the difference is it's stark. I mean, look at this. On the left, you've got RIP. It's slow, it's limited, and it's based on secondhand info. But on the right, you have dynamic routing. It knows the whole map, it adapts almost instantly, it can scale to a global size, and it finds the best path, not just the one with the fewest stops. That ability to adapt super fast is called convergence, and with these modern systems, it's pretty much instantaneous. It's a night and day difference.
So the big takeaway here is that these modern protocols, like OSPF and especially BGP, that's the protocol that literally holds the entire internet together. They're what make our online world so incredibly resilient.
This is why your video call doesn't just drop or your game doesn't lag out just because a construction worker accidentally cuts a cable somewhere. They just find a new route in milliseconds. They can even balance traffic across multiple roads at once to keep everything moving.
All right, our packet has its directions. It's ready to finally leave the local network and step out onto the public internet. But before it can go out, it needs a disguise. It has to change its identity.
This disguise has a name. It's called NAT, which stands for Network Address Translation. And it's a really clever system that takes all the private internal addresses on your network and hides them all behind one single public IP address that your internet provider gives you. This analogy just explains it perfectly. Think about a giant hotel. To the outside world, to the post office, it just has one street address. But inside, of course, there are hundreds of individual room numbers. NAT works the exact same way. The internet only sees your one public IP address, but your router, it knows exactly which internal device, which room number, the data is actually meant for.
Now, NAT comes in a few different flavors, but the one that almost all of us use at home and in our offices is that third one, PAT, or Port Address Translation. This is where the real magic happens. It lets dozens, even hundreds of devices share that one single public address. And it does it by assigning a unique port number to every single conversation, which is kind of like giving each guest in the hotel a unique room key.
So, let's recap. Our little packet found its way out of the local network using the MAC address table, it got its directions using dynamic routing, and it put on its NAT disguise to go public. It has successfully navigated the invisible superhighway.
From that local switch knowing exactly which chair you're sitting in, to the routers all over the world constantly updating their maps, to that final NAT disguise, all of it has to work together in perfect harmony in a tiny fraction of a second.
This table is a great final summary. You've got the MAC address table, that's the local directory. RIP is the old-fashioned way of guessing paths. NAT is the disguise for going out in public. And dynamic routing is that smart, modern GPS that makes the entire internet actually work at the scale that it does.
And you have to remember, this journey we just followed, this isn't some rare event. This is happening billions upon billions of times every single second all across the planet. This is the invisible lifeblood of our modern, connected world.
So the next time you click send, maybe just take a half second to appreciate that tiny packet's incredible epic journey. It really makes you wonder, if we have a system this complex and this fast already running completely invisibly beneath everything we do, what amazing things is it going to enable us to build next? Thanks for coming along for the ride.